Hello, in this video on kinematics, I'm going to specifically look at frames of reference, something which is quite easily overlooked when you start studying kinematics. But it's worthwhile getting used to them now because frames of reference will come back with a vengeance later on when we're learning other topics in physics. So, what are frames of reference? Okay, well, in kinematics, we're trying to describe how points are moving in space. So here's a point in space. It's a point on a two-dimensional space, which is the screen. So if I want to describe how that point is moving around, the first thing I need to do is be able to say where it is. And then I can worry about describing how it's moving. So if I want to describe the position of that point, I can only do that by making reference to some other point. So I might say, with reference to the bottom left corner of the screen, we move a certain distance to the right and we move a certain distance up. And then that will unambiguously give us the location of that point. Now that description would contain three pieces of information. It contains the origin, which is the point that we're measuring from, in this case, the bottom left corner of the screen. It contains orientation, because we need to say what directions we're moving in order to get to that point. So in this case, it was moving right and up. And then we need some kind of measurement scale to say how far we're going in each direction. So we need these things in order to define our frame of reference. Right, so, and we can put these anywhere. There's an infinite number of frames of reference you could use. So if I set up a frame of reference here, I could say this is my origin O, and I'm going to set my two dimensions, because we're on two-dimensional space, the flat screen, in those directions, which are perpendicular to each other, because it fits in with it all fits with our description of flat Euclidean space that we're using, that we can describe everything in Cartesian coordinates, where each dimension of space is independent from each other and perpendicular to each other. And we can describe the location of this point using Cartesian coordinates. So if we were going up in centimeters, this might be, say at coordinates 3, 3. So we've unambiguously defined where that point is. I could have had an origin over here, and I could have put my axes in those directions if I wanted, and I could have measured it in millimeters, but that's fine. I can still say where that point is. It's just less easy to use as setting up my frame of reference in this manner. So that's what frames of reference are and why they're important. And we're going to try and identify these frames of reference when we're going through the example questions, just so we can get practice early on of seeing how they're working. The other useful thing with frames of reference to start learning from the outset is, well, how do we change from one frame to another? Sometimes we might have measurements that have been taken in two frames of reference. We see this where you might have someone taking measurements on a boat and another one taking measurements on dry land. So if you've got those two sets of measurements, then how do you reconcile them? How do you describe them in the same frame of reference? Or we might decide to change frame of reference specifically because it will make solving a problem a lot easier. And we'll see these things coming up. So we're going to start with what's known as Galilean transformations, the transformations between frames of reference that was devised by Galileo back in the 16th century. And yeah, these are simpler and more common sense than other transformations that we'll see when we start moving into modern physics. But, it's best to start with something that's useful and also easier to understand. So let's go back to the frame of reference I had on the previous slide. We had this XY set up. We've got an origin there. We had some point that we were saying is at 3, 3. I'm also going to say that this frame of reference is not moving. So this is a stationary frame of reference. It's got velocity equal to 0. So what if we come over to another frame of reference over here? We say the origin is at O prime. We've got, and I'm not going to change everything, I'm going to leave the orientation the same. I'll leave the scales the same as well. But we've now got a new set of XY coordinates, X prime and Y prime, because we've got a different origin. And I'll set this in motion in the X direction. So it's moving with velocity V in the X direction. How are we now going to describe this point in space in the second frame of reference? How are we going to transform from one frame to the other? All right, so the location of the origin in, I call this one frame of reference 1, this one frame of reference 2. So the origin in frame of reference 1, we'll say, is at some set of coordinates x, y, whatever it would be using those axes in frame of reference 1. The origin in frame of reference 2 is at 0, 0. So we want to go from F1 to F2. So we need to subtract this xy from all of the coordinates of position in order to get the position in frame of reference 2. So if we've started with this at 3, 3 in frame of reference 1, then in frame of reference 2, we are going to be at 3 minus x and 3 minus y. So we need to take those off. So that's how we're transforming from one frame of reference to the other. Similar thing with the velocity. So the velocity of this reference frame 2 is v in the x direction relative to frame of reference 1. So if we're going to say, well, in frame of reference 2, we're going to think of ourselves as being v equal to 0, we again need to subtract this v. So this point here, which was stationary in frame of reference 1, will now be moving at minus v, as in the opposite x direction, the negative x direction, in frame of reference 2. So you can see why these are considered to be more common sense and easier transformations, because we're just subtracting these values. We're subtracting the new position of the origin, and we're subtracting this velocity. So this is like the sort of thing you do, when you're sitting on a train pulling out of a station. Is the train going forwards or is the station going backwards? Well, it depends what frame of reference you're looking at. If you're looking in the frame of reference of the station, then the train is moving forwards with velocity v. If you're looking in the frame of reference of the train, then the station is moving backwards with velocity minus v. It's exactly the same thing that we're looking at here. Is common sense relative motion is what we're going to be looking at. And we'll employ this in some of the questions, the example questions we go through. We'll be able to use it in some of the ones involving bearings and things, where you've got boats floating through water and the water is pulling the boat into a different direction. The current of the water is changing the motion of the boat. So we can look at the motion of the boat relative to the water, one frame of reference, or relative to the land, another frame of reference. So we'll be using those. We'll also be looking at examples where you've got two things moving and you're wondering when they're going to hit each other, because you've got lots of, you've got three obvious choices then for frame of reference. You've got some external point, or if you've got these two objects A and B, well, you could make A the frame of reference, you could make B the frame of reference. You could set the origin of your frame of reference on one of the particles that's moving around. So there's a lot of things we can do. One thing that you'll notice that I haven't mentioned in all of this is accelerations. So we've got changes in position and velocity, but I haven't started accelerating one of these frames. And this is the issue that's really going to come back when we start looking at modern physics, because there are some interesting effects that come into play when you start looking at accelerating frames. In fact, we'll actually look at some of that even in classical physics, where you get the idea of fictitious forces, forces that aren't actually there but look as though they're there because your measurements are within an accelerating frame of reference. But at the moment, we're leaving acceleration out of these transformations, and we're just looking at transformations of position and velocity.